op-amp detector that has the ability to detect the change from positive to negative or negative to a positive label of a sinusoidal waveform is known as a zero crossing detector. More specifically, we can say that it's detect the zero crossing of the applied AC signal. It is basically a voltage comparator whose output change when the input signal cross the zero of the reference voltage level. That is its name so. It is also known to be a square wave generator as the applied input signal is converted into a square wave by the zero crossing detector. Non-zero crossing detector, a circuit that can detect when an input voltage is bigger than or smaller than a given reference voltage, is called a non-zero crossing detector. There are many types of a circuit that can perform this function. The difference among them is in the type of the reference voltage used in the circuit.
Output modeling in a comparator refers to how the input signal from the comparator is connected and utilized within a circuit. The comparator has two inputs, and it outputs a high signal, which is logic 1, when the voltage at the non-inverting input is greater than that at the inverting input. Conversely, it outputs a low signal, which is logic 0, when the inverting input voltage is higher. This output signal can be bonded or connected to various components to trigger specific action. For example, if the comparator's output is high, it can be used to turn on an LED, activate a relay, or send a signal to another digital circuit to perform a certain function. If the output is low, it might turn off the LED, deactivate the relay, or signal the digital circuit to stop a particular action. In essence, output bonding in a comparator is about utilizing the high or low output signal to control other devices and components in the circuit, allowing for decision and action based on the comparison of the input voltage.
Alright, so right now I will explain about the effect of the input noises on the comparator itself. So we know that in practical situation, noise appears on the input signals, and this noise voltage disturbs the input voltage. And you can see the input noise near the 2.5 volt threshold on the graph can cause the output to rapidly change state, which is the noise causes the input to move rapidly above and below of the threshold. And sometimes this can be referred to as a chatter. And we know that this sensitivity to noise can be reduced by the application of hysteresis. And hysteresis is a form of positive feedback that create two distinct threshold levels, which is the first threshold is when the input signals increasing, and the second one is when it's decreasing. So that's all from me. Thank you.
Precision of a temperature sensor circuit to determine when the temperature reaches a certain critical value. One layer of the bridge contains thermistor, which is R1, with temperature sensor resistor with a negative temperature coefficient. Its resistance decreases as temperature increases. The potentiometer R2 set a value equal to the temperature at a normal temperature, which is below the critical value. R1 is greater than R2, thus creating an unbalanced condition that drives the OPAMP to its low saturated output level and keep transistor off. When temperature increases, the resistance of the thermistor decreases. When the temperature reaches some critical value, R1 becomes equals to R2 and the bridge become balanced. Since RT is equals to R4, at this point OPAMP switch to the high saturated output level, turning Q on. This energizes the relay, which can be used to initiate the appropriate response.